Well, how was everybody's break? Cold? Otherwise good? Everybody ready for the exam this week? No? All right. So the exam is just on one chapter. It is a long chapter. And it covers a bit of stuff. This is showing up, right? Exam 2. Exam 2, you can bring a 4-function calculator, a little scientific job. No graphing calculators. Put a big star next to this one. No graphing calculators. Another star. No graphing calculators. You're just going to need it to check like addition and subtraction just to make sure that you didn't make a silly mistake. 1 page, double-sided cheat sheet. Okay. That's it. That's all you really need. In terms of material, it's chapter 4. No Verilog stuff. We haven't talked about that at all. That's hardware description language stuff that we're not doing. So if you're going through chapter 4 and you start to see code, that's not on the exam. It's just chapter 4. Specifically, MIMO circuits, circuits, both analysis and design. So I get to give you a circuit with multiple inputs and outputs, and you tell me what the heck it does, or I tell you what I want a circuit to do, and you design a circuit. And then devices, common devices, half adder, full adder, subtractor, multi-bit and so forth, comparators, let's see, what else? Then we've got any 1 to n to 2 to the n device. There are basically 3 types. The 3 types we have are mux, decoder, and encoder. A demux is a decoder. So decoder, demultiplexer, yeah. So encoder and decoder are opposites of one another. A decoder reverses what an encoder does. A decoder also undoes what a multiplexer does. Okay, multiplexer also a data selector. And these devices you're expected to be able to build big ones with small ones. And also to be able to build the smallish ones. All right. I think that's all of chapter 4. I did comparators, right? Yeah. Comparators probably on the same line as, adders and subtractors, but those really are it. We're just going to be using and analyzing these devices. One more thing. Solving. No, get out of here. I need to. There we go. You can't see what I'm moving around, but it was in my way. Solving functions with those devices. So if I give you a sum of products kind of an equation, I say, hey, I've got this equation, or I've got a few of these equations. solve it with a mux and a few other gates, or solve it with a decoder and a few other gates. Okay, I would expect you to be able to do that. Either of, I'm going to put this in quote, the right size or smaller. What do I mean when I say the right size? Well, if it's a function of 3 variables, a, b, and c, the right size would be n is 3, n select lines or something like that. Or smaller. So if you only have 2 select lines, then it gets segmented into smaller problems. Okay, just like the lab. That's it. Those are the topics. So it's been a week. We've been away on vacation. So where do you want to start? We've got, about 50 minutes. Abe. Priority encoder is a type of encoder. Do you want to go over like what it does, how it's built? Sure. All right. So the thing about a priority encoder is it's all about how you define the problem. If you define it in a nice, concise way, building it becomes pretty simple. So the first thing is priority encoder. Priority encoder. We've got to define the priority. Let's draw a box of it here. A priority encoder takes 2 to the n inputs, turns it into n outputs, and usually we'll have like a valid bit. So there's your 1n 2 to the n kind of setup. Now, in the case of a regular encoder, there are a whole lot of lines of a truth table that just don't make any sense. To deal with an encoder, it's easier to start with a decoder. And for my case here, I'm just going to set n equal to 4. Oops. So these are the acceptable outputs. The acceptable outputs from a decoder, right? If you put into a decoder input, if you put that in, that's what you'll see out on the output. So if you put in a 3, you'll see a 1 out on the D3 bit. That's a decoder. So to create an encoder, ideally what we want to see, if we put this line in, we want to see 3 and 2 and 1 and 0. That's what we want to see. Now with 4 inputs, how many rows would there be in a full truth table that fully described this circuit? 2 to the 4 or 16. So what do we do with the rest of the 12? Sort of implementation dependent. It depends on what you want this thing to do. So you could just say that they're all don't cares. That would certainly be very easy to implement. Okay. But if we apply a little bit of logic to this, we can say, all right, if one of these is more important than the other, that tells us how we can apply our don't cares. Okay. And the way I'm going to do this is I'm going to say that D3 is the most important one. So if I see a D3, doesn't matter if D2 or D1 or D0 are there, we're going to say that we have an output of 3. Now there is one more input that I do want to talk about here, because this might be your A and your B input, but you do have an enable input. So as long as it's enabled, everything works. But if you disable it, it doesn't matter what your inputs are, you'll see all zeros. And that's where my valid bit comes in. These are all valid, and this would be invalid. And then your encoder output here would be don't care. So now we've got a way to work from this, and we're going to say if D3 is 1, our output is 3. If D3 is 0 and D2 is 0, D2 is 1, output is 2. If D3 through D1 is equal to 0 and D0, D2. D3 to D2 is 0 and D1 is 1. Our output is 1. If D3 through D1 is 0 and D0 is 1, our output is a 0, meaning our A and B outputs here. All of these have a valid of 1. Valid is 1, valid is 1, valid is 1. Last step here, if D3 through D0 are all equal to 0, out equals don't care, valid equals 0. It's invalid. It's not valid. That's the functional description of a priority encoder. A straight-up encoder just says this, okay? It only says what these 5 lines are. The rest are not valid, okay? So we don't define these. And it gets even sparser as you go on. If you go up to an 8 to 3 priority encoder, you're only going to have 8 rows defined or 9 rows defined out of 256. So it gets very sparse. So priority encoder says, let's build this up now. If D3 is 1, it doesn't matter what the rest of these guys are. Our output will be 3, with our valid bit being valid. If D3 is 0 and D2 is 1, dyslexia happening there, doesn't matter what D1 and D0 are, we'll see a 2, and that's also valid. When we put both of them there, that with D1 being valid, doesn't matter if D0 is a 1 or a 0 because D1 has priority. We will always show a 1 when possible instead of a 0. And finally, or penultimately here, if we have 0, 0, 0, 1, that will give us a 0 and it's still valid. The last one, and this is sort of to be complete, you have to include this line. If you have all zeros, it doesn't matter which one this is, but it does show that it's invalid. Okay? That's the functional definition of a priority encoder and how I go about thinking about it every time I have to build one of these. So if you were to actually run through this, your logical function for A, okay, this being A right here, you'd look at where it's true and you'd say D3 or D2, if either of these two is valid. You could go through this and with a size 4, you could do a 16-row truth table. You could do a K-map, but you'd reduce down to D3 or D2. Either of these is valid. For B, we have to look at these rows here that are 1. And we could start, we could say, all right, D3 or, well, D1 wouldn't quite work. D1 wouldn't quite work because it would conflict here. So you have to say D3 or something like that. Now you might be able to reduce that down, and in fact you can reduce that down, okay, because of your agreement D3 or D3 not, so that would just get rid of that. All I did was I took this line and took it and put it out. So this would really be D3 or not D2, D1. And if you think about what min terms that applies to, it's easy to handle with a 4-variable case. D3 alone corresponds to the following min terms. Min term 8 through min term 15, because that's all the possible input combinations. Okay. This D2 bar D1, well, when you look at that, that's going to correspond to 10, 11. I should have started earlier. That would be with D3 as a 0. So that would be 2 and 3. And I think that's all that applies to there. 1, 2, 3, 4. Yeah. So when you look at those min terms, 10 and 11 would be 1, 0, 1, 0, and 1, 0, 1, 1. So these two min terms correspond to my first row of my truth table here. And B is 1 in those cases. 2 and 3, 0, 0, 1, 0, 0, 0, 1, 1. That corresponds to this row of my truth table, 2 and 3. So that's how I would go about implementing that. Now the valid bit, the valid is really the easiest one, right? We look at, it's always going to be 1 except for this case right here. So valid is, well, depending on how you look at it, I might say D3 is 0 and D2 is 0 and D1 is 0 and D0 is 0. So if all of those things are true, the answer is going to be 0. And now I've got to clean up my writing here. So that's what I said. If all of these things are 0, then I want my answer to be 0. That's one way of thinking about this problem. Does anybody recognize what you might do to this equation to change its structure a little bit? Yeah, apply De Morgan's to it. And if you do that, you end up with basically the OR combination. So D3 or D2 or D1 or D0. If any of those are 1, we're going to be valid, okay, with the priority encoder. All right. What else can we talk about? Mm-hmm.
On the D3 was D not, D2 not,
Mm-hmm.
D1. Why isn't it D2 not or D1? Why is it there?
To look at that, we're looking at this row to create that term. So the question is, why is it not D2 not or D1? Because we want it to be both D2 is 0 at the same time as D1 is true. Okay, so you have to do both of these things to be in this row. All right, if you think about the numbers between 0 and 15 that have bits D2 and D1 set to 0 and 1, that'll provide you only 2 and 3, or up here, both of these don't cares, that it'll go through those, right? 0, 1 will be part of the don't cares. And that's min terms 10 and 11. 10 and 11, so it'll be 1, 0, 1, 0, that's a 10. So that applies, and that's because, you know, the whole point is we're looking at where B is 1. So we want to make sure that we are grabbing it where both of those conditions occur. D2 is 0 and D1 is 1. Okay? Other questions about this, or we can do a different question. All right, let's move on. And if nobody has any other questions, I will. Oh, okay. Abe.
Modular design is modular design, and there's another one.
Monolithic? I don't think I gave my monolithic speech this semester. But, so I've been pushing modular design, build things out of smaller things. And that is part of this, building larger devices out of smaller devices. And I guess now is as good a time as any to talk about monolithic. Monolithic design is what we've done in Chapter 3. You look at all the possible input combinations and you design a very concise circuit. You can always reduce designs down to a 2-level circuit, okay? Bunch of ands and a single OR. The problem is, to make that large OR gate, you might need 30 or 40 inputs on your OR. So monolithic. Root word mono meaning sick, right? Yeah, you're very sick. Means one. Lithic, stone or rock. One giant stone. Everything is in a giant boulder that is very difficult to crack. That's not part of the monolithic design, but it works, right? Big rock, hard to crack. So it's the idea that you're going to have a giant OR gate, F, and then, umpteen AND gates. You can design any circuit in this fashion, So you could design a priority encoder this way. It is possible, except you'd need 2. You'd need 1 for A, 1 for B, and then 1 for valid. And we actually saw the valid one isn't that bad. It's just a 4 input, D3, D2, D1, D0. Okay, and you can create a monolithic circuit for anything we've done. If I asked you to monolithically design a 4-bit adder, that's 8 inputs, 4 outputs, or 5 outputs, right? We got to carry out. Maybe it's actually 9 inputs because the carry in. You could do it, but you'd have 9 inputs. 2 to the 9 is 512. So you'd have to do that 5 times for the 4 outputs and the carry out. That's 5 outputs. Or we say no. No, we're not going to do that. As a result, you would instead use modular design, which is what I've been pushing the whole time. Use small devices that are easy to test, build them up, and when you build up a larger device from a smaller device, it's still pretty easy to test. So modular design is you just take small muxes, make larger muxes. And maybe you add a little bit of extra circuitry. In fact, we designed multiplexers. Even the smallest multiplexer we designed using a decoder and a little bit of glue logic. When we designed a mux, we took a decoder, which is a 3-input, or rather an n input, 2 to the n output, 6, 7, 8. And then each one of these outputs, we took an AND gate and we put an input there. And then each of these did in fact go into a giant OR gate. So this is technically a mux. These are our inputs here. Those are our select lines. Our enable line not really used in this instance. And then we have our single output F or Y. Take something that you know how it works. Add a little bit of glue logic. Here's my little bit of glue logic. Okay, and of course this AND gate was duplicated 8 times. Okay, that's modular design. And when you do this, and if you think that you're going to get away without doing this during your college career here, you've got another thing coming. Because once you get to the ECE260 VHDL design course, if you try to do monolithic design, you can make a monolithic design of a processor. But the TAs aren't going to help you because it's going to be impossible to debug. It's going to be impossible to even think about what's going on, because to make a small change to a monolithic design means going back to the beginning and starting again. But if you do a modular design, you can piece together components. So that was modular design. It's just use smaller things to make larger things. To finish that sentence, before this question was asked, I can talk about Lab 8 if we have no more questions, but I would take as much time as you can now to talk about the exam. Yes? An 8-bit multiplexer. Was that what you wanted? It's an 8-to-1 mux. So when if I ask you to draw stuff, I will ask you to label things.
So the bit just means the right inputs. So if I say like a 4-bit mux, it would just be 4 inputs.
Yeah, a 4-to-1 mux would be 4 inputs. I mean, remember, all of these devices, you can usually fit them into this pattern. So here's my 1, there's my n, there's my 2 to the n. So saying an 8-to-1 mux implies 3 select lines, because 2 to the 3 is 8. Okay? A mux always implies 1 output. Yes?
Does it mean it's an 8-bit? That's what they're asking. If it's 8-bit.
It would be an 8-bit mux, yeah. Somebody who isn't me might say a 3-bit mux and mean 3 select lines. But in that case, you would ask for clarification. Because, they do make things like 10-bit muxes, but it's really still got 4 select lines. They just don't have the last of the 16 inputs, just to save a little space. So if somebody says, are you, by the way, referring to a previous exam question? Because I might be able to help you better there. Yeah, what exam question are you referring to? The one where I asked you to say it in words?
No, I said to draw it.
Draw it? Yeah, it just means draw it.
Does that have to have select lines though to be proper? Like, should it have an enable?
Well, muxes typically don't have enables. So the thing I was going to say actually before that question was, I will expect you to label all of your inputs and outputs. So you'd have to label, I will usually do something like D0, D7. I won't write all of them, all right? I'm not going to sit there and read your chicken scratch handwriting. But also you might say A, B, C. And what I will ask you to do is say something like, this is the most significant bit, especially if you're doing modular design. It's really important that I know which one is the most significant bit, because if you wire it backwards, everything's going to not work. So when I ask you to say what the most significant bit is, you can just leave me a little note like D7, most significant bit, A, most significant, or something. Something to let me know which order things happen in, okay? Because it matters. So if I have A, B, and C, 0, 1, 1. If you read this in binary, what number does it come out in decimal? 3, yeah. But if C is your most significant bit, you have to read right to left, 1, 1, 0, C, B, A, and that would be 6. So you need to tell me which one is which, okay? And a lot of times the labeling will come after. You'll draw the circuit out and then label it to match what you wired, if you're just in a design phase. So if I say draw a 4-to-1 mux or a 4-bit mux, yeah, that's 4 bits of input. Okay? Other questions? Well, I'll tell you what. I'm going to do a 5-minute talk on the lab, and then I'll pause, and if people have more questions, we can go to that. All right. Lab 8. Lab 8 is plug and chug. They give you a schematic, you build the schematic, and you mess with the schematic. You mess with it and play with it. The first thing it asks you to build, all these figures are in Chapter 5. We're not in Chapter 5, obviously. We're just doing Chapter 4 now. But that's okay, because the goal is to give you some context when we get to stuff. Okay? So the first thing they're going to ask you to build is a cross-coupled latch. This is a vocabulary word. All it means is you're going to take two NAND gates, like this. You're going to hook one of these is called S, one of these is called R. And you're going to take the output of the lower one, and you're going to bring it to the input of the first one. And you're going to take the output of the first one, and you're going to bring it over there. And you're going to call these guys Q bar. That's it. That's all you have to build. It's 4 wires. Okay? Here's where things get different, though. I'm just going to briefly show what happens here. If I put a 1 here and a 0 here, we have to look at our rules for NAND gates, right? Or for AND gates. 1 and X is always 1. 0 ANDed with X is always 0. So maybe I missed this. 1 and X is not 1. It's always X. Right? If you AND something with 1, it might as well disappear. Okay? So let's look at this. So if we do a NAND of this, by the way, if we NAND this, well, we get that. So that's just X bar. This will be 1. So if you NAND something with a 0, we know that our output will be a 1. So then we have 1. So 1 NANDed with 1 is 0. So, okay, that follow this down 0. 0 NAND 0 is still 1, right? So everything makes sense here. Okay? So if I start building a truth table, 0, 0, 0, 1, 1, 0, 1, 1, I can fill this in. Q bar. So if I put a 1 on S and a 0, hold on. Why do I have 2 Q bars in my truth table? So I put that in 1, 0. Yeah, 1, 0. I get a 0, 1. And now let's try something else. So I put a 0 here and a 0 here, because we just sort of picked that one at random. So now I've got a 0 NANDed with 0. So what's that? Okay, it's still a 1. And then I've got 1 NANDed with 0. So what's that? It's 0, yeah. Okay, so that's a 0. And I've got a 0 NANDed with 0. That's still 1, right? So everything is copacetic. So that's a 0, 1. Okay, we're going through this. Let's try the next one. 0, 1. Let me do a little bit of erasing here, just so we don't get confused here. So we put a 0, 1 on this. And what do we have? All right, so 1 NANDed with 0 is 0. 0 NANDed with 1 is 0. So this 0 comes over here. 0 NANDed with 0 is 1. All right, so that changed a little bit. 1. That brings a 1 over here. 1 NANDed with 1 is 0. Okay, so that 0 comes over here. That's a 0, 0 NANDed. Okay, everything's stable now. So what do we have? We have 1, 0. Okay. Seems like everything's it may be a little bit more complicated because we might have to follow this figure 8 pattern around a few times, but eventually things settle out. here comes the real trouble. Okay? Put 0, 0 in here. We have clearly already established that 0, 0 gives me a 0, 1. But let's follow it through. What is 0 NAND 0? It's a 1. So that 1 comes over here. 0 NAND 1. No, 0 NAND.
Yeah, 0. No, so 1. You said 0 and 1.
Maybe I'm just out of coffee. 0 NAND 1 is a 1. Not AND. So that's a 1. So that 1 follows its way over here. Now we have 0 NAND 1. Is a 1. Oh. Well, that wasn't actually the fun one I wanted. So now we've got 1, 1. All right, that's enough to illustrate the point anyway. So it changed. Weird, right? Cool. Maybe? No? All that they ask you to do is build these circuits. And I don't know if I have internet here, if I can actually get to... I have been disconnected, and I'm unable to reconnect. Failure to connect to the server. Okay, I'm not going to be able to connect to it. All they ask you to do is build these circuits. So you can go into Fritzing. Maybe I can get this over here. And you can start building things. So this right here is all that it takes to build that cross-coupled latch. It's a single chip. They then ask you to build on that circuit. Again, they're just giving you the circuit that you have to build. Okay? And it gets a little bit messier, but it's still just one chip. So depending on how you want to do this, you can set up your breadboard so you just move that NAND gate from point A to point B to point C. All of these have, I think, at most 3 inputs. A, SR, enable, D, enable, D, clock. Yeah, at most 3 inputs. So you really only need 3 inputs. And if you wire things in the right fashion, as long as you know that you're only going to be populating one chip at a time, okay, you can, on one breadboard, quickly go through this. I have not, I don't think I have in this example here. Yeah, I don't have any breadboard stuff set up. But you could set it up so that, no, don't do that. Okay. This section right here, that's part 1. And then you have another chip, which you don't actually populate. It's the same chip. Come on. Okay, and that's part B. So you just wire up 4 circuits all along your breadboard. There will be one point where you need to use a 7410 and a 7400. And that's all you get to use for that. You don't need 2 7400s and a 7410. Think on that. And you'll see that I'm right. That's Lab 8. Probably it's going to take you 2 weeks to build and test all of these. You are going to be going back to static I/O for this, though. So you'll use buttons or switches. When it says connect to a pulsar, just a button. All right, it goes 0 or 1. I think that's most of it. So that's what I got. Back to the exam now, and if not, we can keep talking about the labs, but back to the exams. Lab 6 is due Wednesday. Yes. We have lab on Wednesday? Yeah. So it's due, yeah, we're starting lab 8 this week, so it's due this week. Yes? No. That is an incorrect assumption. Other questions? Why are you guys laughing? It's on the syllabus.
I thought, I brought up, I think we can say, oh, you know what, I'm
I think you guys have learned by now that I'm not a nice person. I'm a mean old man who just hates you all a lot and wants to make your lives miserable for no reason other than to make your lives miserable. It has nothing to do with preparing you for future courses or the world. Nothing at all. Okay. So, other questions? We've got time for maybe one more. Sure. Comparators is not a 5-minute topic, but we'll cover what we can. That was weird. You can't see this on the screen, can you? There we go. Comparators. We have 3 types of comparators. Equal, greater than, or less than. So if I were to, in a general form, and this is something that you can look up in your book, so I'm not going to spend a lot of time on this, 2 n-bit numbers, a full comparator, which we never built in class, would have things like a less than output, an equal than output, and a greater than output. If you wanted to augment this with a greater than or equal output, yeah, you just OR greater than or equal to, and there's your greater than or equal to output. It's in the definition of the term. Greater than or equal to is true if it's greater than or if it's equal to. And similarly with less than or equal to. Okay, let's take less than, equal to. And then you'd still have your less than, your equal to, your greater than. Equality comparators are the easiest to understand because each bit must be equal. They are independent of one another. Whereas we saw in class, greater than and less than, it's not independent. Each bit isn't an island. It's much more like a priority encoder, where you say, if the highest bit is greater than, everything is greater than. If the highest bits are equal to, and the next bit is greater than, then it's greater than. And on the way down. So it's just a sliding scale of the first bit equal, then the first 2 bits equal, then the first 3 bits equal, etc., etc. As long as you keep that in mind, you should be able to write down an equation or a description that will help you build that. Okay? And the single bit less than, for something like A less than B, okay? Just if A is 0 and B is 1, it's binary. There's only so many combinations, okay? And the less than function is only true when A is 0 and B is 1. The greater than function, A greater than B, greater than, not a subset of, A is 1, B is 0. So you can use that basic building block, as a greater than block. A, B, greater than. And you can use those, you can build those up. Okay? In fact, you could build a single bit full comparator. I think we'll do that and then we'll call it quits. A single bit full comparator, A, B. Okay? To build that A is 0, B is 1, that's less than. Quality, how did we build an equality comparator? Well, that's A and B equal to 1, but that doesn't cover the case where A is 0 and B is 0. So let's draw out the truth table. Again, because this is a small problem. Yes, hush you, I heard you. 0, 1, 1, 0, 1, 1. So they're equal there, both 0, 0. They're equal there, both 1, 1. They're not equal there. This is the exact opposite of an exclusive OR. So this is an exclusive NOR. And again, just A, B. I'm not drawing the lines. It's just going to get crowded there. And so finally, greater than is A, B, 0. So there's your greater than. So if you're building a multi-bit, let's try for a 3-bit comparator. I think that should be enough. Greater than, equal to, less than, greater than, equal to, less than, greater than, equal to, less than. A3, B3, A2, A1, B1, A0, B0. This would be a full 3-bit comparator, giving you both the greater than, the less than, or the equal to. So down towards the bottom here, our full equal to is only going to be true if all of the bits are equal. So that's all, that's code word for and. Like that. So there's our equal to logic. Our greater than logic has a couple of different ways it can be true. First off, let's go to a different color. If the most significant bit is greater than, we're definitely going to be greater than. Otherwise, okay, we have another option here. If these two bits are equal and the next one is greater than, well, then we're all set. The third option, if the first two bits are equal to one another and the least significant bit is greater than, then we're good. Those are the only ways that we can have a symbol that's greater than. And if I were to build the less than circuit, you'd see a symmetry across this. Let's do it in green. Okay. If the most significant bit is less than, then obviously both numbers are less than. Second option here, if the first bit is equal to, ooh, this is gonna get messy real fast. This is where a schematic CAD package would be very handy because you can move these things around until it looks a lot neater. Okay. So that's one option, right? If the first bit is equal, second bit is less than. Excuse me. Finally, where do I grab it? From here and here. Those are the first two being equal, and then the last one being less than. There's your less than input. There are ways to optimize this. Like, I have a lot of lines going along that I don't really need, because once I could create up a cascade of equal bits, so I could have, so then I wouldn't have to have quite so many lines. I did this in a rush because I know we're out of time. We're actually over time. Try this, see what comes out of it. Okay, and you could extend this to more bits, starting at the left, working your way to the right every time. So, as a reminder, if you came in late on the exam, 4-function or scientific calculator, no graphing calculators, 1-page double-sided, bring plenty of pencils, erasers, etc. It's on all of chapter 4, not counting the Verilog stuff.